everyone, welcome back. We'll continue the discussion of the wave equation in higher dimensions. So last time we obtained a solution of the wave equation in 3 dimensions, n equal to 3, looking for radial solutions. When initial data itself is radial, so it's natural to look for a solution which is also radial, and that motivated us to look for spherical mean function of a given function. So we'll continue the discussion of the spherical mean function. Okay, so again just I'll recall the definition of the spherical mean function, and this we have already seen in the discussion of Laplace and Poisson equations. So a very useful tool. So that is just given any function from Rn to R, you just define this spherical mean function by taking the mean of the function, given function h, over the balls around a given point x. Okay, sometimes it's also useful to write thinking this as an operator. So instead of m of h, so we'll think m as an operator. So that's equal to okay, I will write it like this. Okay. So we'll write this m sub h as m of h, thinking that m is also an operator. That will be useful sometimes. So given any function h, so this mean value operator m produces another function with one extra independent variable r. Okay, and then by change of variable we rewrote the spherical mean function, and so some important properties we discussed. So the important property is this Darboux equation that connects the Laplacian of the spherical mean function with a second order derivative of the same mean value function with respect to the extra variable r. Okay, so that is an important thing, and now we'll see how that can be exploited in the study of this wave equation. Okay, so before coming to this wave equation, let's do some computation. In all these things, computations are bit lengthy, but they are straightforward. Okay, so now we are given a function of two variables x and x. X is in Rn and t is positive, and now we form its spherical mean function. Okay, so now this will be a function of x r t. Okay, so we are taking the spherical mean only with respect to the x variable, so this is just Let me write it again. So mod j equal to 1 u of x plus r j. So this is surface integral on the unit sphere. Okay. So as such, if you notice here, this integration with respect to j variable. So if u is smooth, so I can simply take this del square by del t square directly. Let me take that mu xrt. So this is simply 1 by sigma n mod j equal to 1. So utt, two derivatives. So you simply take the differentiation under the integral sign. And similarly, if you notice at the x variable, this x variable and j variable, that is variable of the integration, they are also not coupled. So this we immediately obtained. So this, let me stress now, mu. Before that, so this is nothing but the spherical mean function of utt. Okay, so if we think this as an operator, so this will write this as, okay. So the second derivative with respect to t variable of the spherical mean function is same as the spherical mean function of the second derivative of u with respect to t. So that's what it says. Okay, so let me remove this. So this, in other words, we write this as, okay, so this operator of differentiation and this m, okay, they combine. Whether you first operate m and then take the derivative, that's what is left hand side, or you take the derivative first and then take the spherical mean function, they are same. Okay, and same thing happens with the x variable. So this, just let me stress that mu xrt is nothing but, let me again write that, if x and j were coupled, so we cannot do this, but since in the integrand x and j are not coupled, we can do this. And that is same thing as m of x. Okay. So the importance of the Darboux equation now comes into play. So Darboux equation relates the Laplacian of the spherical mean function with respect to x with this operator. Okay, so now you apply the Darboux equation. So this one, by Darboux equation. So this equals to 1 by r to the n minus 1, this operator del by del r of r to the n minus 1 del by del r of mu. Okay. So if you perform the differentiation and expand it, so this simplifies to, so del square by del r square plus n minus 1 by r del by del r. So this operator, second order operator, acting on m. Okay. So now suppose u is a solution of the wave equation. Suppose utt minus c square. So let me just stress that dependence. So this is only with respect to x variables. And now you take spherical mean on both sides, okay, of this entire thing. So spherical, so since this is just an integral, so it's a linear operator. Okay, so this is just m of utt minus c square, that's a constant, m of del x u. And now look at the computations we have done, and this is just d square by dt square mu minus c square d square by dr square plus n minus 1 by r d by dr mu equal to 0. So if u is a solution of the wave equation, then its spherical mean satisfies this equation. So this is our first observation. Okay, and in this equation notice that so x plays only a role of a parameter. So the spherical mean function now satisfies again a second order equation, but in only two variables. So that's what we want, because we somehow want to reduce the whole analysis again to one dimensional wave equation. So again we can apply D'Alembert's formula and other things. Okay, so that's our goal. Okay, so we have achieved now. So this, look at here. So the spherical mean function of u satisfies a second order equation, but only two variables. Okay, so that's important. T and R. Okay. So what about the initial conditions? So initial conditions are prescribed on the solution u at t equal to 0, and again taking the mean value. So they transform to initial values for the spherical mean function, and that's what I have written here. So taking the spherical mean function of the solution u, we just saw that it satisfies this equation, and this has a name. It's called Euler Euler-Poisson-Darboux equation. Okay. Again, if this term, this first order, okay, this is just del r is, so I'm mixing that, same notation, del by del r. So if this first order derivative were absent, then we simply get uh, a wave equation in one dimension. But in the presence of this, so there are some difficulties, and that we already seen. So again we go back to the case n equal to 3. Okay, n equal to 3. So these, the initial conditions at t equal to 0 on u now are transformed to initial conditions for the spherical mean function. Okay, so this initial conditions at t equal to 0. Okay, so here, so let's similarly here, so we are given these initial conditions of u, and now we are just transforming them to r. So again, first consider the case n equal to 3. We'll come back to the general case of n later, because the transformation is little more complicated. So for n equal to 3, it is very simple one. So again, you put v of x r of x, so the function of x r t, this r into mu x r t, and as we observed earlier, so this v satisfies this wave equation in one dimension. And what are the initial conditions for v? They are almost same as this spherical mean function mu, okay, except for this factor r. Okay, so v of x comma r comma 0 is r m mean value of phi, and the first derivative of v at t equal to 0 is r m psi. So again, you just observe that x is just a its role is only as a parameter. Okay, now we satisfy this wave equation in one dimensional wave equation with these initial conditions, so we can immediately use the D'Alembert's formula and write down the solution. Okay, so these are the initial conditions. Okay, just here. Okay, so this is first part coming from the initial condition at t equal to 0, and this is the derivative. Okay, so this is just by D'Alembert's formula. Okay, now we want to rewrite this little bit. So here, so recall this, the mean value function is an even function of r. Okay, so that we already observed just by the definition. So this m phi x r minus ct I can write as ct minus r. Okay, so to keep the same notation here, so I want to write ct minus r also here, but that produces a negative sign. So that's what I have written here. Okay, so there is no, this is same as m phi x r minus ct, but this one I write as ct minus r. So it will be clear why you are writing that. Okay, and again same thing. So this is an even function, and we are multiplying by an odd function xi. Okay, so this is whole thing is again an odd function. So if you substitute and do some work, so we can replace this r minus ct by ct minus r. Okay, so that's what is the observation. Okay, and this r is coming because of this v. V is r mu, so mu is V by R. Okay, so V, there is no R, so we just divide by R, so we get this here. Okay, so we have obtained a formula for the spherical mean function of the solution. Okay, and from there would like to get a formula for u itself. Okay, and this is where again this usefulness of the spherical mean functions come into play. So if we take the limit as r goes to 0, we get back the original function. So this is what we have to do. Okay, so we have to take limit of this right hand side as r goes to 0. So there is r in the denominator, so we have to exercise little care there. So let me just okay, do one by one. Okay, so first let me take that first term. What happens to the limit 1 by 2 r of this function ct plus r m5 x ct plus r minus ct minus r for that. M phi of x ct minus r. Okay, so what is this as r goes to 0? Okay, just we want to convert this into a derivative. So how we can do that? Just so if you have any function, so this is just one variable function. So we know that the derivative is simply limit f of. So this is plain definition function of one variable. So this is also equal to limit f of x naught plus h minus f of x naught minus h by 2h. Okay, and we are in such a situation. So here is our function. If you take this ct into m5 xct, you take that as the function. Okay, and then you apply this formula for the derivative. So what we get is derivative of t into yeah, simply derivative. Okay. So this is simply just work it out. So this is d by dt of t so just use this definition of the derivative, you will get that. The second one is much easier, so that's the integral. Okay, so here it's just the integral, so you get just the uh, mean value of this integral. Okay, so this let me write that. So 1 by, so limit as r tends to 0, 1 by 2cr integral ct minus r ct plus r j m psi xj dj is equal to 1 by so that there is a c there. Okay, let me write that c. Okay, this ct m psi x. Maybe there is a 2 there. Okay, and that just simply comes to t m psi x. So as I said, computations are a bit lengthy, but they are straightforward. Okay, so thus the solution of IVP, so finally we can write that UTT minus c square Laplacian u equal to 0. Remember, we are dealing only in n equal to 3, so let me just stress that. Because this is not the formula for generally n. Okay, so this initial conditions with initial conditions u of x0 equal to pi x, u sub t x0 equal to psi x, again x in R3, has the representation okay, so let me write that u of xt is equal to t m psi xct plus d by dt of t m phi xt. where m psi and m phi are the spherical mean functions of psi and phi. Okay, so we can express directly in terms of that. So this is just t by, so in n equal to 3, sigma 3 is just 4 pi. So let me just write that. So integral mod ct psi of x plus ct chi ct dz, and similarly this one. So d by dt of this big expression, t by 4 pi integral mod j equal to ct phi of x plus ct chi ct ds chi. So these are surface integrals. Let me not forget that. So this is ds chi. So again, by change of variable, we can write so this is 1 by 4 pi c square t surface integral y minus x equal to ct psi of y dsy. So this is the surface measure on this surface. So y that variable plus d by dt of 1 by 4 pi c square t y minus x equal to ct phi of y ds. So again, just I will stress, so this is the formula for n equal to 3. Okay, just remember that. And so even though this looks very simple one, so the verification, okay, so verification that u satisfies u is a solution of IVP. Okay, so that's not straightforward, so it requires some work, requires some computation. So for example, even verification of the initial conditions, so straight away we cannot put t equal to 0. Okay. So because there is a t in the denominator, so we have to only take this as limit as t goes to 0. So that requires work. So even just verification of the initial conditions is not straightforward in this case. So in the case of D'Alembert's formula, that was very straightforward. Okay, but here we have to do some computation. So we have to take the limit. Okay, and in the next class we will further analyze what this solution and what are the qualitative properties of the solution. Uh, Again, domain of dependence, range of influence, and we'll also come across the Huygens principle and what does that mean. Okay, so we'll discuss all these things in the next class, starting from this representation of the solution in n equal to 3. Thank you.